Welcome everybody to the fourth unit of the first week in the Parallel Programming Concepts course in OpenHPI. In this unit we want to talk about parallel hardware classification so that we can have a common terminology when we talk about parallel hardware units and parallel hardware architectures that are available in the field. When we take parallel hardware today and the different ways of building such system, there's a variety of ideas and concepts. You can talk about parallelization and parallel hardware on a very low level, like with multiple cores in a processor. You can go one level higher and say you have multiple processors per system. You can then go again one level higher and combine different machines into an overall installation and call this a parallel machine, like in the high-performance computing world. So the problem we are facing when we are talking about parallel programming concepts is that we need to decouple ourselves from the underlying hardware model a little bit to not only talk about threads on cores or threads on processors and other variations. And our proposal for this course is that we use a terminology by Tim Madsen, who is one of the leading experts in parallel programming in the field. And Tim Madsen made a definition of a couple of terms that helps in talking about parallel hardware while not binding yourself to a particular implementation of this parallel hardware idea. So Madsen says that the starting point is a program, some piece of code, some application you want to run, and inside this program we have a couple of tasks. So the program, the programming language, the developer defines tasks, and these are units of your software that may be able to run in parallel. And these tasks now are expected to run on your parallel hardware in order to speed up the overall execution of the application. So the thing that takes the particular piece of code and wraps it, encapsulates it in order to be runnable on a core or on a processor, this is something that we call an execution unit. A typical example from the software world would be threads and the according implementation of their functionality. So if you take a standard program, like for example in C, you would write a function, and in this function you have a piece of code that executes a particular task. This task can now be run by the help of a thread, and this thread then can use a particular hardware resource in order to run in parallel with other tasks that are wrapped by threads on the system. Another option would be to take the task and put them into separate processes inside the operating system. So the execution unit varies in different approaches, but the idea is always to take a task and represent it as something that runs concurrently or even in parallel on a system. The third thing that is introduced in this terminology model is a processing element. And a processing element is a piece of hardware that is able to run one execution unit at a time. The most prominent example today for processing elements are cores inside a processor. So multiple cores give you multiple processing elements that can run multiple execution units at the same time. But you could also map processing elements to the concept of logical processors like we can find in Intel hyperthreading, or even to whole machines. So the execution units give you an abstraction, as processing elements as execution units give you an abstraction of how modern hardware is able to parallelize your code, and you can now think about parallelization strategies without actually referring yourself only to one approach in this area. There are also other aspects that we will discuss later in the course, especially in week 2, and these are synchronization and race conditions. How do you do faster processing by the help of parallelization? This is, for most of you, hopefully an obvious idea. We take a particular program and we split it up into different tasks and now let these tasks run in parallel on a set of processing elements. So the idea is to exploit more cores, more processing power from the CPUs you get today by defining tasks in your software, in your programming language, or maybe by the help of a particular library. This software then is enabled to formulate different tasks that can run concurrently and then hopefully in parallel on the hardware. And then you deliver this program, you run this program on your piece of hardware, and you get an improved speed for your application. The traditional way of dealing with such parallel architectures and to abstract such hardware is something that is called Flint's taxonomy. So parallel computers are not a new idea, but they have a long history of hardware trends and developments. And therefore, in the early 1966, Michael Flynn defined a taxonomy for ways how parallel hardware can deal with instructions and data in order to get a faster processing. So this is a general categorization of how parallel hardware works with instructions and data. And this is so commonly known that you can still find the acronyms and the terminology in today's literature. So let's have a look into how Flint's taxonomy works. There are 4 classes of parallel hardware, of parallel processing. The first one in the upper left corner is single instruction, single data hardware. This is a model where it said that you have a single instruction or a stream of instructions, a sequential stream of instructions, and you have particular data items. And in a single instruction, single data system, which is also called SISD, you can process one instruction with one data item at a time. So basically, this is pure sequential execution. There is no parallelism here in the execution. You just have a sequential evaluation of the instructions and the application of the instruction on the data. The second approach you may find is called SIMD, single instruction, multiple data. In these systems, you have the situation that you have still one instruction or one instruction stream, and you have multiple data items. So one single instruction can now be applied to multiple data items at the time. This is a capability that is built into the hardware, so the hardware has all the mechanisms and the preconditions to perform such an activity. The data items to be processed by the same instruction could be, for example, a vector. So this is a classical thing that you can find in, for example, SSE technology in processors or in graphic cards and GPU accelerators. The idea is always that we take a set of data and we apply the same instruction to all the elements of this data set, and we get one result. The third class in Flint's taxonomy is multiple instruction single data hardware, MISTI, where we have multiple instructions and all of them are applied to the same data item. This is something that is rarely used in practice, but has some usage, for example, in the fault tolerance domain. And the fourth class in Flint's taxonomy is the multiple instruction, multiple data class, where you have a set of instruction streams and different data streams, and now some of these instruction streams can work on some of these data streams at the same time. This is what we know as today's multi-core hardware and the commonly known hardware, where you are able to run multiple threads or multiple control flows at the same time in parallel on one piece of hardware. So all modern processors you can find in desktop systems and in server systems are MIMD systems, because they're able to run parallel activities at the same time on the same piece of hardware. This slide gives you again a summary of the idea. So the most interesting aspect here is that Flint's taxonomy is a general description of parallel hardware capability. You can take this and apply it to a processor chip and ask yourself if you either have a SIMD or MIMD processor here, but you could also go and apply this classification idea to a compute cluster and ask yourself, do I want to do SIMD computation in this cluster, or do I want to do MIMD computation in this cluster? At the end, the question is always, how do you deal with multiple instruction streams and multiple data streams? Are you able to process some of them in combination at the same time or not? SISD systems is a traditional concept that can rarely be found in today's systems, maybe in some embedded systems. The majority of today's standard processors are MIMD processors, and in GPU accelerators we typically find the SIMD approach. Okay, since Flint's taxonomy now gives us a classification of how parallel hardware looks like, the next question is, how can we deal with these different kinds of real parallel systems? You see in this picture that you can find different combinations of processing elements and memory that help you in building a parallel structure. So on the left side we have the first idea of a program that consists of multiple tasks, according to Matsson's terminology, and now we want to run these tasks on a particular processing element. This is the classical concurrency idea that is implemented in operating systems. So the processing element is a core or a processor, and it runs our different tasks interleaved. The second idea would be to have multiple of these processing elements in the same system, but they're all attached to the same main memory. And the third idea is to have a couple of nodes, a couple of machines, and they are connected by a network. And now you start to distribute your tasks to these different nodes so that they can run in parallel on multiple machines in order to solve the overall programming task. The idea here is to show you that parallelism, parallel hardware, can be implemented on different granularity levels. So you can choose wherever you want to have this on a very fine-grained level with processors or on a large-scale level with networks and machine clusters. When we take now a view into terminology and acronyms used today, this is really hard to get because many people start to use acronyms for the particular parallelization strategy. So this slide here tries to give you an overview of how modern acronyms work. When we take a particular processor chip, something you can buy in the shop or you can buy from Intel, a meanwhile established terminology for this chip is socket. In order to avoid the confusion between cores and multi-core and many-core and SMP or not, the idea here is to say a socket or a processor chip is something that you can plug into a particular socket that can then be used on the main board in order to get some computational capabilities. Inside one processor chip, you may have a concept that is called chip multiprocessing, CMP. And chip multiprocessing is the acronym for describing that you have actually multiple CPUs on this chip. And these CPUs are now called cores. So a chip multiprocessing is the acronym that describes what is also known as multi-core or many-core processor, where you can use completely independent parallel activities and tasks at the same time on one processor chip. The next thing that is established as terminology is simultaneous multithreading, SMT. And simultaneous multithreading is the interleaved execution of tasks on one of these cores. So now you have the situation that you have multiple cores per chip, but each of these cores might also be able to run tasks in parallel or at least concurrently when we talk about the real implementation. And this is called simultaneous multithreading. And the more common terminology for that is hyperthreading, which is a market term by Intel. So you can have a concept that is called logical processors. One core is implementing multiple logical processors, and now threads can run in a concurrent fashion on this piece of hardware. When you now combine the chip multiprocessing approach and the simultaneous multithreading approach, you sometimes see that this leads to a term called chip multithreading, CMT, and so which allows you to run multiple tasks or, for example, threads when you talk about the execution unit on such a processor in order to gather concurrency and parallelism in the execution. When you now take multiple of these chips and you put them on one main board into one computer, you get something that is typically called multiprocessing. So multiple processors inside a system, and this is also the classical approach of parallel hardware before we started to see multiple cores in one chip. One commonly known term for such a scenario of multiprocessing is SMP, symmetric multiprocessing, which basically declares that all the processor chips that are built into your mainboard are equal. So all of them can perform the same kind of work. And if you now go one level higher in the granularity, you end up with something that is sometimes called a multi-computer. So you can now take multiple of these processor chips, put them into a machine, but now you can also combine multiple machines. And with multiple machines, you get something that is called a multi-computer in the case where you run one parallel application on this set of distributed resources. When we take a modern processor chip and try to map these concepts into the layout, you get something like this picture. So you have here a picture of a real modern processor, and there you have multiple cores. Each of the cores has its own cache, but inside the core you have instruction level parallelism as a mechanism, and you have SMT as the mechanism for implementing quasi-simultaneous execution, for example, by hyperthreading. All these cores together with their SMT capabilities, but also with the capability to work with each other on the same memory, then form a CMP system, a chip multiprocessing system, that allows you to run a parallel piece of software on this one processor chip in order to gather some speed up.